a software engineer at Groq, and I'm a little bit more on the application side. I'm relatively new. I started just over 6 months ago now. And my background is in physics, where I was doing lattice QCD research, which is a more traditional HPC application. And so today I want to talk to you just kind of set the scene and just go over what I mean when I say latency, throughput, and scaling, and talk about compiling and optimizing some small models for throughput with our compiler. And I just want to go over a very simple thought experiment to get all our heads on the same page. And then I'll go over 2 specific case studies with some small molecular transformers. So there is a difference between latency and throughput, and not all applications are throughput critical or latency critical. It really depends. So right now we're picking up a lot of steam in the media because our LLM inference speed is so fast, it's really low latency. When you go to our chat website and use it, the response is snappy and fast. And so this is obviously a big area where low latency is a thing that's important to the user. There are latency critical applications in science. For example, at Argonne National Lab, there's the advanced photon source, which is being upgraded, and it's going to be upgraded in a way that's going to create an extreme amount of data. And one option is, of course, to store it, but that has its own problems. And so people are trying to analyze the data directly off the detector and only store directly analysis results, as opposed to the entire database where there might not be interesting signals for gigabytes or terabytes of data. Another example is for tokamak fusion reactors. To control making stable plasma is the current challenge. And so if you want to keep a plasma stable and you have access to controlling the magnetics field around the plasma and all of the other parameters of the reactor, then you need to be doing this as quickly as possible. So this would be another low latency critical application. Traditional HPC applications aren't so latency critical. They're only latency critical up to the point that a researcher can do them in a reasonable amount of time, hours, days, weeks even. So as long as it doesn't take years to do, we don't really care too much if it's a minute or 2. So I just picked 2 examples. One of them, fluid dynamic simulations, are massive HPC allocations. And what I'm going to talk about a little bit later is making predictions of molecular properties. In this regime, I'm going to say the order of magnitude wrong, but the general order of magnitude is an estimate, and it's huge. It's there are roughly between 10 to the 30 and I think 10 to the 60 are things I've seen in papers, numbers of molecules. And obviously, if we're designing some kind of drug for cancer or material that's really strong for building stuff, that's just an unfeasible amount of space to search. So we really want to process as many molecules per second as we can. So of course, in the traditional HPC sense, what people look at when trying to parallelize applications and make them run faster are strong and weak scaling. And I think the audience has a pretty general background, so I'll be a little bit brief here. You can pause me and ask a question if you need. Anytime throughout the talk, I should have said already. But the 2 things we'll look at for our molecular models later on is both strong and weak scaling. So strong scaling is when you fix the size of your problem. And for the sake of this slide, let's just imagine you're trying to compute the forces on some string, and maybe you pretend that you simulate the string as being 100 points all connected together. Then fixing the problem size would be fixing the 100 points on the string. And then you pick an algorithm you want to do. You figure out how to parallelize the algorithm, and then for the same 100 points, you'll run it on 1 processors, 2 processors, 4 processors, 8 processors, etc. And the ideal speed up for 2 processors would be 2, for 16 processors would be 16. In practice, this can't be achieved. 1 is because the entire program might not be parallelizable, but 2 is communication. So usually in most HPC algorithms, you actually have to communicate information that one of the processors is computing to some of the other ones. And so you'll get this degradation. And usually, I mean, a 16 times speed up if it's an application that takes a month. 30, let's go 32. If an application takes a month to run and you can speed it up by 32 with like a 10% efficiency loss, like that's a pretty good trade-off. Weak scaling, on the other hand, is where you increase the problem size with the number of compute resources. And so imagine, for example, we started out with a string with 5 segments and 1 processor. We could go ahead and do that computation. Weak scaling would be to when I have 2 processors, have 10 points. When I have 4 processors, 20 points, so on and so forth. And the difference here is that strong scaling eventually, I guess I should have said, breaks down in the really, really high limit, because eventually, if you only have 100 points, 1,000 processors they'll be doing a tenth of a point each, which is a very inefficient way to be doing calculations. So on the other hand, weak scaling efficiency, you never run into this bottleneck at the very large processor limit, because when I get up to 1,024 processors, I'll have 5,000 points, and everyone will be doing their own 5. Still, though, all of these processors need to communicate the information about its little local string to all of the other ones. And so you'll end up getting some inefficiencies. And an important thing that'll come up later is that these assume fixed implementations for the algorithms you're looking at. And we'll talk about why that may or may not be the case later. But these 2 kind of expectations are based on fixed implementations. So how do we do neural networks on the Groq compiler? You heard earlier today by Philip that if you have some neural network, essentially all this is it's a graph of computation. So you take your inputs, run it through operator A, operators B and C, and then operator D, and then operator E. And the thing we want to do for throughput, at least, is optimize how many inferences per second we can do with the model. And there are 2 things we can control extremely easily, just using the compiler as a command line tool. And also by having access to the model and being able to change the batch size one. So we can actually change the size of the problem. So this would be something we would do in weak scaling. And we can also change the number of cards, which is what you do in strong scaling. And we can just add that as a flag to the compiler. And the thing that becomes interesting and not obvious about looking at scaling experiments is that there are both inter-op parallelization strategies where you can maybe compute B on one chip, C on another chip, and intra-op parallelization opportunities. So I've tried to give a little diagram here. So imagine this is a batch, like this is some vector with 3 elements, so batch size 1. And you can compile the model on a single card. It fits, it's a small model, which are the ones we're going to talk about in a little bit. And then you have some output. So if you decide you want the runtime to be faster, you could go ahead and try to compile it. It may or may not be faster depending on the model. But for example, maybe the compiler will decide, hey, inter-op partitioning is the best choice. So with a batch size of 1 and 2 cards, this might run a little bit fast, or it's the best the compiler can do, whether or not it's faster. The thing that's interesting is that the compiler isn't going to fix its implementation of how it evaluates the neural network when you, for example, change the batch size or change the number of cards. And the one easy way to think about this is because the amount of data it has access to do the computations on changes. So for example, if you increase the batch size, maybe it makes more sense to now intra-op split operators A and B, as opposed to keep them both on a single card. And so the simple compiler experiment I'm going to walk you do and show you some examples of to see what the best throughput is to, on the one hand, increase how many Groq cards you have, because this can change, for example, how much inter-op partitioning is done or intra-op partitioning is done, and also the batch size on the other hand. So to be accurate, what I want to maximize is the number of inferences per second, IPS. And how to compute the number of inferences per second is, let's say you have a batch size, which is in units of like how many inferences you're doing. So every time you run the input-output program that the compiler and assembler give you, you'll do B batches and it'll take L latency seconds to do it. And then, for example, if you have a whole rack, then if you have a whole rack with n LPUs, which is in that case would be 72, the one model you'll see I'm only going to actually just stop it at 8 chips divided by G is how many times you could run it on all of the LPUs you have access to, whether that's just you allocate a node for a couple of hours or allocate 4 nodes for a couple of hours. You can try to find the best setup for this. So I think now I'm going to actually go ahead I'm going to skip these slides. These are just, I'm going to do some stuff on the terminal. So these are just put up here for reference. And I'll take a break for a second just to check that there's not any questions about what we're doing. I don't think I can see the chat at all. So, oh, there is the chat. So Christian asked, I guess, yesterday about production inference serving solutions at scale. Yeah, so the one, I guess, I don't know much about the Triton inference server or doing stuff kind of over like network APIs. The one thing is that because our hardware is deterministic, the batch size also has to be fixed for every compile. So if you compile an IOP and you want to run 4 inferences on a card at a time, you have to specify that upfront. The compiler, the card has to know, like at every point in time, how much data is on it and where it's going.
Chris, one came in right before the break by Boyd. Do the model weights reside distributed over SRAM in a static configuration? Are they loaded into model initiation, then reused for each token?
Yep. So they are loaded onto the card. And as long as that model as long as that process is still running and your card is still allocated, the model weights will stay on there. And you could keep doing multiple inferences on there.
Right, and then there was another one. I don't know if you can see it or not. It just came in. Relevant to batch size, any follow-up on?
That was the one I answered first, actually.
Oh, okay. Okay, yeah. I saw that. Yeah. Right.
Oh, and then Chris, if you can hear me, this is Christian Kaufner. I asked about Triton and the batch sizing and what have you.
Yeah.
So the deterministic nature isn't necessarily a problem. There's needless to say, like various like queuing and padding strategies that you can deploy, and that's kind of Triton does very similar things to that actually, and that's kind of one of the things that's of particular interest to me in terms of essentially making particular Groq hardware more widely consumable with network APIs and such across like multiple users and disparate sessions, those kinds of things.
Yeah, I think that would be a question more for somebody that's working like with our cloud team or the API side then, unfortunately.
Yeah, and right now, Christian, the cloud API is probably the best that we have in relation to that. We're working to get that same cloud API experience into the ALCF as well. But right now it's in the Groq cloud.
Cool. Yeah, that's perfect. I assumed that needless to say, this was implemented somewhere internally for Groq Cloud. I'm particularly interested in being able to enable similar functionality while also essentially self-hosting on Groqrack or internally maintained hardware.
Mm-hmm. Yeah, it is possible. It's as our racks become more and more, become available, we're going to give the same experience that you would have from the Groq cloud from an on-prem perspective. That's the goal. So it's not just buying a rack, you're buying a solution from that perspective to have those capabilities.
Perfect. Thank you.
And then there was one last one, Chris. Is there a way that chat questions can be compiled, or never mind? We'll answer that one separately.
Yeah, cool. Yeah. Sweet. So before going over, I'll continue then. And before going over the terminal, I just want to motivate these molecular languages. This would be in response also to Alfred's question earlier. So molecules are, composed of atoms, and they're held together by chemical bonds. And in real life, there are these 3D objects. They might have some very complicated structure. Who knows like what geometric shapes they have. Lots of them have lots of different symmetries about them. And so there are definitely a lot of non-transformer based architecture attempts to these. The most popular two being are graph neural networks or message passing neural networks. And graph neural networks kind of, if you look at this picture of a molecule on the right-hand side, you can see why a graph neural network might be a good choice. Molecules are pretty much a bunch of nodes and edges or vertices and edges. There are also people doing convolutions. I am not well versed enough in molecular science to know why convolutions were a thing people tried. But people are also trying convolutions. And then the reason people are also trying transformers to molecules is because you can represent them with a sequence of characters. And apart from things like H2O, water, which is the way we talk about them, there is a more concise representation, and there are several. Smiles isn't the only one, but you can represent not only the important atoms that compose molecules. So in this case, like ethanol is CCO. Another molecule, benzene, which is 6 carbons and 6 hydrogens, can either be represented. It has 2 different structures, one of which is a double bonded structure, and that's represented by these equal signs. So this language of molecules, if you will, not only represents the atoms, but it also represents types of connections between atoms, and it can also be used to represent rings. So that would be like this loop over here. And so, to my surprise, as not knowing very much about molecules, is this is something that actually can end up working quite well. And essentially, it's just because it's a language problem. It's a language modeling problem, and this is exactly what transformers are excellent at. So I'm going to now go over to kind of do some stuff on the terminal just to try to, this is like, maybe hands-on is a bit generous. I'm just going to walk through my thought process on how I went ahead and ported a model. If this text isn't big enough, I could try making it a little bit bigger. So otherwise, I will start showing some stuff off. So first of all, I got this model from people at A&L, actually. They were interested in it. So kind of the first thing I usually do is find out whatever file is doing the inference, because we're mainly an inference like provider. So I wouldn't look for any files that have anything to do with training or pre-processing or anything like that. I would just go ahead and look for where inference is done, which I happen to know is this file. And within the file, the first thing I do is I try to find where the actual model gets defined, which for example is here. So once I know where the model is, and I know the model is loaded, and I know what Python name it's called, I don't need anything else. All this is, as far as porting the model is concerned, not important. And if it's your model, this should all of this bit in here should be really familiar to you. So for example, like all of that stuff would get deleted. I wanted to do smiles.py. And since this is I do have to do some typing live. Since this is a TensorFlow model, unlike I think in general we try to vouch for PyTorch, but the other option is Onyx. So for any machine learning model you have, as long as you can convert it to Onyx, it has a chance of working with our compiler. And in TensorFlow, if you print the model, you'll get a bunch of information about it. So we'll do that really quickly. Of course, you have to, set up Python, make sure everything works. So here is the TensorFlow output of our model, so we can kind of learn some things about it. So I told you I'd be looking at some small molecular models, and this one, I hope you agree, is small. It's 8 million parameters and only 30 megabytes, and our card has 220 megabytes of SRAM. So surely this model will fit. Maybe naively, you would think I have about 220 megabytes. Surely 7 of these models can fit on a card. So we'll keep that in mind that, hey, as far as SRAM is concerned, roughly 7 models. And this might not be exactly true because of intermediate tensors. So we don't just have to store all of the trainable parameters. We have to store all of the intermediate tensors going through the, or not all of them. We always have to store some intermediate tensors going through the model. In TensorFlow, then, when you print the model, you'll get a bunch of information about it. So this is called the people at ANL that I've been talking to about this have always called it a simple smiles transformer. And I think that becomes apparent because there's an input of none, 45, which in TensorFlow, the none being a leading index is the batch size. So this is a number we're going to have to specify before exporting to ONNX. And the shape 45 is the maximum context length. I happen to know that this is passing in tokens directly. So the tokenization step is done before this step. Then there's token and positional embeddings being done. So you can see the embedding size is 128, also much smaller than large language models. You can see here a bunch of transformer blocks. There are 5 of them. And then there are essentially just a bunch of dense layers. So dense layers. And at the end of the day, what this model is doing is a regression type problem, and it's predicting some molecular property. Again, I'm not the expert on the molecular properties. I just know it's outputting one final number. So this is great. This is super helpful. The most important thing we actually need is this bit of information here. And we need to know how to port the model to ONNX. So I said I've been at Groq 6 months, and before that I wasn't doing machine learning at all. So all I did was Google it. And if you, on the ONNX runtime page, if you Google TensorFlow to ONNX, you'll find a couple different libraries to do it. Which one do I want to go to? And usually I'll make some special Python script that specifically just converts the model to ONNX. This is especially nice for easily changing the batch size. So I'll go back to where I was before. So before I said I printed out the model. I also load the weights. That way the model is actually correct. Here you'll see I'm just setting this batch parameter to 1 for the first time. And then I'm specifying some amount of input dimensions. So the input dimensions are going to be a tensor with leading dimension batch size and second dimension 45, and the output tensor is 1, 1. And for this model, there's this package called TensorFlow to ONNX that has a convert method that takes in a model. And then I see this part is actually from a different way to convert the TensorFlow model. Sorry, that could be actually, oh no, I see, I'll use that in a second. For the TensorFlow to ONNX Python package, the second argument you need to do is a list of all of the inputs. The name also has to match because TensorFlow is going to be looking for named tensors. You also need the data type and the size. Then, as long as that works successfully, you can save the model to ONNX. And at the bottom, I do some other stuff, like, for example, I trace over the ONNX tensor. The tracing specifically updates all of the input and out dimensions of all the operators. And I'll show you the neton graph of this so that you can see what this model looks like, and what kind of parallelizations we can expect out of it. The only other thing that happens is pretty typical in machine learning, like optimizations, is converting the model to FP16. So I am happy to go ahead and run that. I think it'll print out the whole model again, and then it'll do a bunch of other stuff. This part here is it actually going ahead and tracing through the model with the inputs. This won't take very long at all. Perfect. And there's a bunch of warnings you see about casting float 32s. The warnings are good. I'm going to be happy with those warnings. And then hopefully you heard yesterday that Netron's a great way to visualize neural networks. If not, now you do know. So if I open up the smiles.onnx file, we can go ahead and open it up in a browser. I'll do that and pull it over. Okay, so now we can go ahead and look at the neutron graph for this model, and it's a simple transformer. But you'll see my scroll wheel here is actually quite long. And indeed, the model is quite long, and I would say relatively narrow. What this means is that yes, I will zoom into the neutron graph in a second to look at some of the tensor sizes. Let me actually just first zoom out, just to really make it clear that this model is long, and I think that's too far out, actually. Really, this model is quite long and quite skinny, and there are many segments of, I'll zoom in a little bit more. There are a lot of segments of just where there's not going to be any inter-op partitioning, and there's going to be segments of complicated operations like GEMMs where there's just no inter-op partitioning to happen. So that's already a sign that maybe parallelizing this model isn't going to be particularly useful. Furthermore, you'll see that a lot of these tensors, so this is a result of tracing the input and output dimensions of the tensor. You'll see a lot of these intermediate tensors are also quite small. And we're doing things like adding up with a bias that's a 21 by 128. So these are relatively small and probably maybe not even going to be very well intra-op partitioned. Of course, the only way to know that is to go ahead and compile the model. I already transferred it onto the ANL rack. So I'll go ahead and run the compiler. For the sake of showing you a little bit like extra, I'm just going to go ahead and compile it for 2 chips. So the way to do that is to include, I'm just going to go up, a flag titled -- multi-chip. And then there are a bunch of specific flag options, which I've listed in the slides. So this DFA14 2-chip string means I'm doing 2 chips, and the DF stands for Dragonfly, because within a node, the chips are Dragonfly topology. And then I'm also going to add a bunch of statistics. Specifically, I'm going to look up some power and utilization statistics from this compile. And I'm also going to save some of the stats for some processing. And this is just, then the last flag is just the Onyx file. So I'll go ahead and run this. And it does take a minute or 2 in case anybody wants to type out a question. I will maybe try to make this one bigger. A flag I've omitted here. Oh, go ahead.
I was just going to ask, in case anybody's thinking this, I hear you put multi-chip flag on there. And if they didn't know the multi-chip flag existed and they just did it for a single chip, how would that work out?
The same, I mean, yeah, so it would compile, or it would at least try to compile it on a single chip, provided the memory requirements were less than like 230 megabytes, they would just go ahead.
Okay.
You'll see that at the end, there's an easy way to tell how many chips you've compiled for.
Okay.
The default is a single chip.
And we have some of these flags listed in the GitHub under compiler flag.
I think so under the Groq flow, and I guess I can also show that there's a help option. So basically, all of the operations have been scheduled. It's now printing out a bunch of utilization statistics, and then a bunch of compilation statistics. So the easy way to tell how many chips you've compiled it for is whether or not there's a single .aa file or multiple ones. So if you just have smiles.aa, it's compiled for 1 chip. If there's a dot and then an n, a bunch of numbered ones, that's basically an input-output program that's going to be or an assembled program for all of the chips. And then I think Sanjeev talked yesterday about how you can use the assembler manually. So this is the compiler, again, just produces Allen assembly files. They need to go into then the Allen assembler, which is either AA latest or AA multi-chip. But for the sake of analyzing the throughput of the models, I don't actually have to get into all of this. So we can go ahead and already get some information about the model. So first of all, the statistics are that one is you get the cycle count, and we of course know like the clock frequency of the chip. So the cycle count can be used to tell you the latency. You also get access. It just tells you what the peak on-chip data memory usage was, and you'll see it's 23 megabytes. This is less than the 30 megabytes we talked about before, because the 30 megabytes was printed in float 32 or float 64, and this has been downcasted to float 16. We can also see the performance stats for each chip. And one thing you'll want to know immediately is that the last compute cycle on chip 0 is 89,137, aka one before the last compute cycle of the program. And the last compute cycle on the second chip is -1. And that's because the compiler decided not to do any parallelization of this model. It decided it was better not to be doing C2C communications. And part of the reason for that, we can kind of figure out if we go up to the utilization report. So for example, I pointed out that there were some GEMMs in this model, and they were happening in a way that can't be interop partitioned or anything. And the peak utilization of the MXM unit for this model is 100%. So there's just some point along the compilation where we don't have any MXM resources available. Also, similarly, the VXM resources, the memory resources, the streaming resources, these are at peak times over 50%. And during those times, then we wouldn't have the resources for much else to be going on. Yeah, so again, the compiler gives you access to all of this information. And of course, we can then go ahead and do what I said before, where we can go back to the, I will close the Netron graph. We could go through, and I've of course not going to do all of this online. But we can go ahead through and make a bunch of different Onyx files with a bunch of different batch sizes. And we could go ahead and do compiles with different flags for the multi-chip, and we can collect all of these statistics, which is what I'll show now back on the slides. So slides show. Okay, hopefully the slides are visible again. So the first thing I wanted to look at was we can look at is strong scaling, and you can imagine what the difference is going to be, which is that adding more cards, as I just showed you, doesn't really change anything. Here, the only difference is that I've used, to generate these points, the flag effort is high, as opposed to the default is standard. So that's the different optimization levels that Philip talked about. And so there's really just like no benefit for this particular model to be parallelized across multiple cards. So what about the other dimension is, what about weak scaling? This is where we increase the batch size and the number of processors. And you can see something interesting happens, that going from 1 inference to 2 inferences by batching barely increases the cycle count, whereas going to 4 triples the cycle count from 2, and then going up to 8 again almost doubles the cycle count going from 4. And we can furthermore, so this is already a sign that probably something good is going to happen here with the number of inferences per second. And as it turns out, the best configuration for inferences per second is a batch size of 2 with a single chip. So here's just plotted a heat map of these inferences per second, which is essentially if you had access to, in this case, just a single node, 8 cores, and you compiled a program to take in 2 inputs and run it on a single card. This is how many inferences per second you do, versus if you were to use all 8 processors on a single inference, on a single batch input, you would be running 10 times slower. And this table just repeats the same things in case the colors aren't super clear to everyone. And this is something I mean, I think is pretty obvious from looking at the Neteron graph. There's not really any interop partitioning. And when you try to compile it and do a parallelization, you can see clearly the statistics that say whether or not, for example, how much the functional units are being utilized at again, there's on average and on peak, but once you hit a peak point, you can't be doing too much more without slowing down how long the program takes. So that was the simple smiles transformer. I'm now going to talk about a very, let's see, as user concurrency increases. Yes, I think Venkat presented at a conference this year some results of throughput for this model. There was a slight decrease, of course, because of at that point, once you start actually accessing all this stuff, you know, you have a lot of system stuff going on. I don't remember the specific, like, what number they got compared to this, though, off the top of my head. But if you wanted to message me about it, I could try to like remember or look it up. Yeah, so of course, like, yeah, if you actually, when you actually scale it up, then systems start doing things, CPUs start having to send data, stuff like that. But nothing significant at the very least, to my recollection. So on to a slightly different model. Is this model is called high DRA. It's some hierarchical transformer model. This is a picture from the paper. So there's some part at the top, which is, as far as I know, doing some feed forward dense neural network. It's taking the outputs from that and then passing them into two different sets of attention modules. So one attention model is taking in information about gene expression. So there's like two different like sets of inputs here. Once this gene level network, once this first set of attention modules gets evaluated, the output is again passed back into another attention module, and then eventually some molecular characteristic is computed. So rather than going back to the terminal, I've kind of botched up the output a little bit from TensorFlow. The model again is really small, even though this diagram looks a little bit more complicated. There's only 2 million parameters, so even smaller than our first one. And everywhere where I put these like dots in boxes signifies that there's a list of like 50 to 100 different things that are happening, like all in parallel. And we can see that again from the Neteron graph. So on the left-hand side, I've zoomed into like one of these specific like lines in this area of dots on the left. So for example, this glycolysis line might do something like, I guess I could have went through and found it, but like there's a lot of them. I would only just realize I could have actually found the exact one to really make it a nice consistent story. This extends out like 50 to 100 wide. You can see how many lines there are on the top and bottom. So the top is the input, and then the bottom, everything gets concatenated together, like I said, for the output. The good news here is that we can actually expect parallelizing across a lot of chips is going to produce a lot of opportunities for interop partitioning. So I'm going to show you the results on two different like software development kit releases, just because we've had some nice improvements and some of the stories change. This is just to like help motivate you that like if you're not happy with a specific amount of inferences per second, like not to worry. The compiler team is still making progress on doing things. So this is some 0.10 version, which is not what's currently on the ANL rack. What's currently on the ANL rack is 0.11. So here we can see the strong scaling, which I can't really brag about. You know, when I doubled the amount of LPUs, I only decreased the cycle count by like 25%. Not really mind-blowing stuff. It doesn't really get better going up to more LPUs. This is, yeah, I mean, it is what it is though. So again, like this is the kind of situation where if this is some latency critical application and you need it to happen in under 30,000 cycles, then throwing up the 8 chips at it does still at least provide a little bit of a difference. For the weak scaling of this model, something really interesting happens, which is that as the number of cards and batch sizes increases, we actually have an extreme improvement on the cycle count. And this is, I think, the first really non-trivial thing that happens. And it's important to, and this is why I stressed in the explanation of weak scaling, that the algorithm and the implementation of the neural network is not fixed across all of these different dots, because otherwise you would never be able to exceed 100% efficiency. Technically, going from here to here, we have 200% efficiency. But again, this is because the compiler is going to do more inter-op-partitioning or maybe some intra-op-partitioning. It's going to do whatever it needs to do. Pretty much the story is the same on the current version of the SDK. Not as dramatic as needing to do a batch size of 32 with 32 cards. So I guess let me also stress too that, like, you know, if you are using our systems and really want to do something in production, you might be, oh wow, it compiled, I'm going to start going. If you were going to run it for a week, you could instead run it in half a week just by trying these compiler experiments. And on these small models, the compiles take a minute or two per dot, so nothing too extreme. Maybe towards like 60 batch size of 64 and 64 chips, it might start going towards the 5, 10, 15 minutes. But again, this is just a one-time cost to find out whether or not it's worth it. On the current version of the SDK, we're actually doing first of all, if you look at this y-axis, you'll see the cycle count start at 80,000. On the current version of the SDK, we're somewhere around 40,000. So that's already a nice little speed up kind of like for free, that you as like an end user don't have to do anything for. The strong scaling actually goes a little bit better also, which is nice. So 46,000 to 26,000 is much closer. It's like 80%. I think I did the numbers before. This jump to this jump is like 80%. This one to this one is 60%. But again, this is expected for strong scaling, that at very large number of processors, you're just going to be communicating and not actually computing very much on any one resource. For the weak scaling, things shift the most. Specifically, it turns out it's much better to run 2 inputs with 2 chips. That's just what it is. The main takeaway I want to take from all this is that this is all completely model specific, right? And so I can't tell you a priori. I could come up with some guesses about like what's going to happen on the cards. But ultimately, I think just running these compiler experiments is really like the way to go to optimize whether it's latency or throughput. I would say just try a bunch of compiles. That's the end of the main like results on like the throughput and scaling. I'll take a second if there's any questions. And if not, I will proceed to just like a quick couple other applications just to like highlight some things that are possible that people are working on.
I don't think I see any questions. Penny had asked about performance, if the performance is maintained with 1 chip and 2 batch as user concurrency increases, but she said thanks. So yeah, so you were able to answer.
I got it. Yeah, okay. I mean, I didn't have a specific answer, but yes.
Okay, awesome. I think that's it for now. I'll cool. I'll keep checking the chat as well.
Cool. So these are, of course, just some transformer models. They're not the only type of architecture that the compiler or the hardware supports. So this high DRA model I showed you is actually part of a bigger project called the Improve project. And this is an attempt to look at the drug response prediction of cancer cells. And it's a curation and standardization of essentially benchmarking not just attention-based models, which are what I just showed you examples of, but also graph-based models, which makes, of course, sense for molecular models, and also convolutions. And I guess here, if you're familiar with maybe molecular science, you can see why a convolutional network is going. They're like one hot encoding, essentially like atoms in different types of bonds. Yeah. So this is just some of the other stuff we have going on. And in general, I mean, arbitrary machine learning workloads is like part of our goal, which is why Sanjeev talked to you yesterday a little bit about like ML agility, and that's what the goal of like Rockflow is. And we're doing stuff not just with large language models, but also computer vision, general linear algebra, anomaly detection, and also you saw a bunch of the scientific ones. I wanted to say a little bit more about like one of the low latency ones, this X-ray detector signal processing. Specifically, the next set of X-ray resources will be 100 times brighter, and they're going to have a terabit per second bandwidth off the chip. This is the plan, at least, to have a terabit per second bandwidth off the chip, producing 16-bit resolution, 256 by 256 images. I don't know the numbers offhand, but just, yeah, this is something that actually like our card alone isn't going to be able to handle. It's actually something we're trying to co-design with FPGAs, where the detector will get the data. There'll be a little bit of pre-processing and orientation of the data like on the FPGA, and then that will actually communicate the data directly to the Groq card, preferably via C2C, but like if not via PCIe, of course, depending on whether or not PCIe is even fast enough for this kind of rate. Some of the types of models they're interested in are these. So one of them is an encoder. So essentially the problem they're trying to do is analyze images of X-ray beams. So essentially they want to do like peak finding and information finding. The goal is not to save these actual images, but save what the images mean in terms of the science and the physics that's going on. So the peak finding algorithm is a convolutional neural network, and this is an encoder decoder network. Again, I'm not too much of an expert in these, but these are things that can be quite complicated traditionally, and in this case need to be done extremely fast. As like a teaser to like things that are a bit definitely like beyond the scope of so far this workshop, but if people are interested in, definitely like reach out and let us know. There's this, we have a quadratic unconstrained binary optimization solver. And the Cubo problem is mathematically is given up here in the top right. I can also say that this is what the D-Wave style quantum computers solve, is they solve specifically, they're physical systems that solve these types of problems. And we're not solving this problem exactly. Instead, what we've done is come up with, or I guess borrowed this thing called an SB solver, which is called simulated bifurcation. It's essentially a goal to simulate the minimization of this algorithm. And this is some situation where it is an iterative algorithm. And since our hardware is deterministic, you can't say run for 10 or 20 or 30 iterations. So we're able to design situations where both the CPU host can be driving the Groq card. And the use cases for this are either portfolio optimization for financial portfolios, what stocks to invest in when, and how much of your portfolio should be invested in each of them, and also traffic route problems. So rather than everybody taking the one highway and clogging it up, is how should the traffic kind of naturally divert its courses so that there's even traffic nightmares across all of the roads, I guess, if you will. And that is it. Thank you for listening.